Hi comrades, welcome to the next video on metallic bonding. This should be video number 2 hopefully. In this case we're going to continue on with our metallic bonding. We've talked about the lattice and now we're going and the properties of metals, and now we're going to try and make the connect between the metallic bonding model and the properties of metals. Let's see if this works. So we should be able to use the model to explain many, not all, but many of the properties of metals. Otherwise, what's the use of having a model? And this is our current model. If you go back through the history of science, there's probably been other models that have been have evolved, been proposed and rejected through the years. But this is our current understanding in physical science. So, first property is luster. And so what happens, here's our cations, here's our delocalized electrons whizzing around in our metal, and what happens is, why is a metal got a lustrous appearance, or has a luster? It's because the light is reflected off these delocalized electrons. These mobile electrons actually bounce off the light in the form of photons. And it's an interaction that is way beyond the physical science understanding, but that's just how it works. So it does explain the luster. And again, the light ray bounces off delocalized electrons. You can pause this and read all this. It might help you understand. Okay, and it also says down here, close packing of the metal cations prevents light passing through the metal. That's why metals are opaque. So the light bounces off, it can't get through. Ooh, did I go one too far then? Yes. Conducting heat was a property. So how does it work? Well, here's our metal rod, here's our delocalized electrons and cations. We heat this end, causes the cations to vibrate, and that causes the electrons to vibrate, and the electrons gain kinetic energy. That's the energy of motion, so they actually move faster, and because they're moving faster, they have collisions or near collisions. They get close enough to each other to transfer energy, and that bumping occurs within the delocalized electrons, and it spreads. So the kinetic energy moves through the metal rod, and at the end, we feel it in the form of heat. Just another model. Here we are applying heat to one end, causing jostling, and the cations and the delocalized move. So pause this and make sure you read all this. And in the end, the whole lattice structure is jostling with energy. It's not collapsing, because if the jostling was so energetic that it would break apart the lattice, that would be the transition from a solid to a liquid. So we're not doing that, but they're gaining enough energy to get hot. Okay, and you can see this transition occur when you make metals glow with different colors when you heat it up. So metal starts off as dark. Think of your stovetop or the heater element in the bar element in a heater. And then if you turn it on and heat it up, it starts to go red, and then if it gets really hot, it goes white. And that's all part of this gaining in kinetic energy and giving off heat. It's transferring kinetic energy into heat energy. What about conducting electricity? Well, if we applied a potential difference across the two ends of a piece of metal, what would happen is the electrons would experience a force, because they'd actually find themselves in what's called an electric field, and they would move towards what's known as the positive end. And this movement of electrons, because remember that the valence electrons or the delocalized electrons are all free to move, they're not attached to a cation, and so we get what's called a current or a flow of electrons in a certain direction. And I think the next diagram highlights that a little bit more. So here's our piece of wire, there's our cations, and you have this end attached to the negative end of the power supply, this attached to the positive end. So effectively there's an electric field that forces the electrons, or the electrons really want to move in the electric field, basic physics, and you get a flow or a current or a gradient of electrons. And so the more electrons that flow, the more current you have, basically. And the faster they move, the more voltage you have, is one way of thinking about it. Again, pause this, there's a lot of words there. Pause it and have a read. Make sure you understand it before you move on. Malleability and ductility are very similar and explained by the same principles. Here's our lattice. We apply a force to it, and because the whole structure is effectively lubricated by the delocalized electrons, the cations can move and slide past each other without getting too close. And so unlike ionic substances where everything's locked in place, and if you flex it they get too close and they force apart, in a metal they move and slide. So basically the sea of negative electrons or delocalized electrons act as a lubricant to allow the cations to slide past each other. Again, this diagram, they're hitting this, it's a little micro hammer hitting just one cation, and it causes it to jump across without getting too close that it would actually break it. Melting point and hardness, well, that just tells you that the metallic bond is quite strong. And the melting points and hardness increase with the increase in the number of outer shell electrons. So if the metal starts off with a lot of outer shell electrons, it will then shed those, and so you'll have a lot more delocalized electrons, and because that's sort of like the putty or the cement that holds it all together, the more delocalized electrons you have, the more energy is required to break the metallic bond. So there's a relationship between the number of valence electrons and the melting points and hardness of the metals. Density, that's just telling us that the metal lattices are closely packed. Remember that slide of the oranges? That's closely packed. If the oranges were separated by a big distance, that's not closely packed. So basically closely packed means that you can't fit any more in. It's as close as it can get. So that's why they're dense. So let's just look at a quick problem relating the uses of metals to their properties. Here's a whole list of metals. This is straight out of your textbook, chapter 5. We've got the symbol, the density, the melting point, the heat conductivity, the electrical conductivity, and the hardness. And the question we were asked is, using this, decide what properties of aluminium make it suitable for saucepans. So if we looked at aluminium, it's dense, it's in the middle. There's things that are denser like lead, you might know, gold and silver. So it's not too dense, it's actually like magnesium, not that heavy. It's got a melting point 600 degrees, which is pretty good. It conducts electricity with a high value, up there with copper and silver and gold, but you wouldn't want to make pots and pans out of silver and gold. Some pots and pans are made out of copper, which is interesting as well. And electricity, pretty irrelevant really, because we're not going to plug it in. It's not the metal itself that's conducting electricity. We're after heat conductivity. Hardness is medium, so certainly you wouldn't have anything that's soft, because you'd be using metal appliances in it, and something too, you can get hard. So if you looked in a kitchen, you would find pots and pans made of aluminium, copper and iron. And the advantages of aluminium are that it's got a high heat conductivity, it's malleable, high melting point, and has medium hardness. So that's why you find pots and pans made out of aluminium. It suits the needs. And mainly also it was relatively cheap to make nowadays. So you should now be able to do questions 6 and 7 in the textbook. Question 6 uses that table, looks at why you would choose it, choose different metals for different things, and the next one looks at why all those power lines around the countryside are made of aluminium rather than copper. So have a go at those questions. And the next video is looking at some alternative explanations for things that that bonding model doesn't actually fully explain. Alright, cheerio.